Imagine trying to find meaningful patterns in a vast, sprawling city where every single building is its own separate, unique landmark. It would be incredibly difficult to see the overall structure, wouldn't it? Now, picture condensing that entire city into a clear, understandable map that highlights only the most important features like main roads, districts, and key attractions. This simplified map still captures all the essential relationships, but in a much more digestible way. That is very similar to why low dimensionality is preferred for embeddings in machine learning. Low dimensionality for embeddings is preferred primarily because it helps machine learning models generalize better, reduces computational overhead, and effectively mitigates the challenges posed by the phenomenon known as the curse of dimensionality. It allows for a more efficient and robust representation of complex data, capturing essential semantic or relational information while discarding noise. The core reason behind this preference lies in the concept of the curse of dimensionality. As the number of dimensions or features in a dataset increases, the amount of data needed to ensure statistical significance grows exponentially. In very high-dimensional spaces, data points become incredibly sparse, making distances and densities less meaningful. This sparsity makes it harder for algorithms to find true patterns, often leading to overfitting, where the model memorizes training data noise instead of learning generalizable relationships. Low-dimensional embeddings act as a powerful form of data compression, distilling complex inputs like words or images into compact vectors that retain only the most salient information, making it easier for models to learn and generalize. To practically achieve and leverage low dimensionality, practitioners often employ techniques like principal component analysis or autoencoders during the embedding generation process. For instance, when creating word embeddings, models like Word2Vec or Glove learn to representing words as dense vectors, typically ranging from 50 to 300 dimensions, for fewer than the vocabulary size. These models are specifically designed to find and encode the semantic relationships between words in this compressed space. The goal is to ensure that words with similar meanings are represented by vectors that are close to each other in this lower dimensional space, facilitating tasks like text classification and semantic search. An interesting aspect of these dense, low-dimensional embeddings is their ability to capture analogies. For example, in a well-trained embedding space, the vector relationship between king and man can be remarkably similar to the relationship between queen and woman. This property, often referred to as vector arithmetic, arises because the embeddings are optimized to representing not just individual meanings, but also the nuanced semantic relationships between them in a highly compressed and efficient manner. This intrinsic structure in a low-dimensional space unlocks sophisticated forms of pattern recognition and reasoning for machine learning models. Ultimately, opting for low-dimensional embeddings empowers machine learning models to learn from data more effectively and efficiently. By focusing on the most informative features and reducing the noise inherent in high-dimensional representations, these models can build more robust internal representations, generalize better to unseen data, and perform complex tasks with greater accuracy and computational speed. It transforms vast amounts of raw data into a structured, meaningful, and usable format that is ideal for advanced artificial intelligence applications.